It is this chemical reaction. A nitrogen gas molecule plus 3 hydrogen gas molecules gets you 2 ammonia gas molecules. This is the Haber process of binding nitrogen molecules in the air to hydrogen molecules, or turning air into fertilizer. Without this reaction, farmers would be capable of producing enough food for only 4 billion people. Our current population is just over 7 billion people. So without the Haber process, over 3 billion people would be without food. You see, nitrogen, in the form of nitrate, NO3, is an essential nutrient for plants to survive. As crops grow, they consume the nitrogen, removing it from the soil. The nitrogen can be replenished through long natural fertilization processes like decaying animals, but humans want to grow food much faster than that. Now, here's the frustrating part. 78% of the air is composed of nitrogen, but crops can't just take nitrogen from the air because it contains very strong triple bonds, which crops cannot break. What Haber did, basically, was figure out a way to take this nitrogen in the air and put it into the ground. In 1908, the German chemist Fritz Haber developed a chemical method for utilizing the vast supply of nitrogen in the air. Haber found a method which took the nitrogen in the air and bonded it to hydrogen to form ammonia. Ammonia can then be injected into the soil, where it is quickly converted into nitrate. But if Haber's process was going to be used to feed the world, he would need to find a way to create a lot of this ammonia quickly and easily. In order to understand how Haber accomplished this feat, we need to know something about chemical equilibrium. Chemical equilibrium can be achieved when you have a reaction in a closed container. For example, let's say you put hydrogen and nitrogen into a closed container and allow them to react. In the beginning of the experiment, we have a lot of nitrogen and hydrogen, so the formation of ammonia proceeds at a high speed. But as the hydrogen and nitrogen react and get used up, the reaction slows down because there is less nitrogen and hydrogen in the container. Eventually, the ammonia molecules reach a point where they start to decompose back into the nitrogen and hydrogen. After a while, the two reactions, creating and breaking down ammonia, will reach the same speed. When these speeds are equal, we say the reaction has reached equilibrium. This might sound good, but it's not when what you want is to just create a ton of ammonia. Haber doesn't want the ammonia to break down at all. But if you simply leave the reaction in a closed container, that's what will happen. Here's where Henri Le Chatelier, a French chemist, can help. What he found was that if you take a system in equilibrium and you add something to it, like say nitrogen, the system will work to get back to equilibrium again. Le Chatelier also found that if you increase the amount of pressure on a system, the system tries to work to return to the pressure it had. It's like being in a crowded room. The more molecules there are, the more pressure there is. If we look back at our equation, we see that on the left-hand side, there are 4 molecules on the left and just 2 on the right. So if we want the room to be less crowded and therefore have less pressure, the system will start combining nitrogen and hydrogen to make the more compact ammonia molecules. Haber realized that in order to make large amounts of ammonia, he would have to create a machine that would continually add nitrogen and hydrogen, while also increasing the pressure on the equilibrium system, which is exactly what he did. Today, ammonia is one of the most produced chemical compounds in the world. Roughly 131 million metric tons are produced a year, which is about 290 billion pounds of ammonia.